Hi everyone, my name is Marcela. I'm a postdoc at Universidad de Santiago de Chile, and I want to talk to you about the work we've been doing within our team. So I first want to present our group here. We're a very interdisciplinary team of teachers, astronomers, physicists, educators, and the idea here is to have regular meetings in what it's called a learning community, so that we can share ideas and knowledge, and we can develop in this way different workshops and activities for the students. And the aim of these workshops is to bring the astronomical research that is happening in Chile and around the world into the classrooms, with the advantage of having real astronomical data. This is data that is being used by astronomers in their day-to-day research, so that the students can use this kind of data, so that they can get to the same conclusions that astronomers are getting to, and have the same kind of conversations they're having. So I will leave here a QR code where you can check out different workshops that are ready to implement into the classrooms. And I also want to share here the kind of work we do. This is a paper that came out very recently, led by Ruben Montesinos. This is the idea of this paper was to take exoplanetary data and have the students apply Kepler's law to that data. So usually when Kepler's law is thought in high schools here in Chile, it is talking about like something that happened a very long time ago. But with this kind of activity, you can have kids realize that, oh, this is actually an equation that is still relevant, it's still useful in day-to-day research, and you can apply it to discoveries that have been made every day. So going now back to the title of my talk, what is our place in the universe? I of course don't pretend to answer this question in 5 minutes, but we can take this question very literally. For example, we can say, what is our place in the universe? Well, we're in planet Earth, in the solar system, going around the Milky Way. But this is probably not what people think when they're asked this sort of questions. So humans have always had this kind of questions, and ever since we discovered that we are not the center of the universe, we have wondered, like, are we special in any way? Are there other worlds like ours out there? And of course, astronomy is very well equipped to answer these kind of questions, because over the past few decades we have discovered over 6,000 exoplanets. And so exoplanets have become like part of science and not just science fiction. And also, especially here in Chile, we have very nice telescopes. That, for example, this is the ALMA observatory, and you can take pictures of protoplanetary disks, which are the structures of gas and dust surrounding the forming young stars, where planets are being formed. And so what we want is for students to also be involved in this kind of conversation that are happening in academic circles. So to do this, we have formed a new learning community, especially focused on exoplanets and planet formation. This was the topic of my PhD thesis, and we're planning to have many meetings with this new group over the next few years, and hopefully develop the same kind of workshops and activities that I showed you before. Now focusing mainly on planet formation, a topic that hasn't been addressed that much, like usually when people teach astronomy in high school. So I'm gonna give you an example of one of the workshops we've been developing. This one is the one that gives the name to my talk, Our Place in the Universe. So here our aim is to compare the exoplanets that we have discovered with the planets in our solar system. So for example, you can organize the exoplanets into this kind of graph. You can organize them by mass. This is important because you can distinguish them between rocky planets, Neptune-like planets, and then gas giants. And you can also organize them by distance, like here, which is important, for example, if you want to talk about like habitable zones. And you may notice a pattern here that most of the exoplanets we have discovered are in this upper corner, and the planets of the solar system are in the opposite corner. So does this mean that planets in the solar system are rare? Are we special or unique in some way? Probably not. Probably this is just a bias in the way we are detecting exoplanets. So this gives a nice opportunity for students and teachers to discuss about the different detection techniques. Why do we need better and different detection techniques that discover other kinds of planets? Because usually with the detection techniques that we have right now, we are biased towards planets that are closer to the star or planets that are very massive, because those are generally easier to detect. Another thing you can do is to take data from the size and the mass of these exoplanets, plot them together, and you will find this sort of relationship between these two variables that is like broken into three separate parts. And these are associated with different populations. These are rocky planets, Neptune-like planets, and gas giants. And this tells you a lot about the internal structure of this kind of planets. I'm just gonna give an example with the first population. These are the rocky planets or Earth-like planets, and if you think of them like in a simple model of just a sphere made of rock, you can calculate their mass by multiplying the volume of the sphere times the density of, say, like rock. And so you have a simple model to explain this relation. And if you do this, if you see the trend line for these exoplanets, you will find that the slope of this line is almost 3. It's not exactly 3, and this has to do with the fact that planets do have layers and they are denser in their center. But this is the point where you can add some more nuance to your models and start to discuss, oh, why isn't it exactly 3 as we expected, right? You can also overplot the planets in the solar system here, and they fit very nicely within the exoplanets that we have discovered. And you can do this with all of the planets on the solar system, and you will find that they mostly lie very nicely within this kind of plots, which tells you that planets in our solar system are similar in their structure to the exoplanets we're discovering. So we can use what we know about the solar system to better understand exoplanets, and what we learn about these exoplanets, we can then take it back and better understand our own solar system. So that's the kind of conversation we're trying to foster here. Finally, I'll give you just a final example. You can also compare the system as a whole. So we have discovered many planets orbiting the same star. And so now you can compare the whole solar system with other stellar systems. And if you see like the top system here, is the solar system, and you can compare it to the bottom three systems, and you may find like they have a very particular ordering. This is what's called a piece in a pod architecture. I like to think of it like ducks in a row, and you can describe this kind of architecture, of this kind of ordering, using geometrical progressions, for example. And then you can ask, like, why do these systems have this kind of architecture, and why does the solar system, why doesn't have like this kind of arrangement? And it probably has to do with the giant planets that we have. And then that opens up the question of how systems evolve with time. How do planets affect other planets, like giant planets are affecting the inner rocky systems. And yeah, so we're still working on this workshop. So we hope you stay tuned. You can see what we do in our Instagram account in Millennium Gems. And you can, of course, contact me with any questions, and you can ask questions right now, of course. So yeah, thank you. Thank you very much.